Hello dear students, I am Professor Priya Kulkarni from Parvatibai Genba, Mose College of Engineering, Wagholi, Pune. Here we'll see one numerical on design of one-way prestressed concrete slab. In the previous lecture, we have learnt about the design steps and what are the conditions required to design the one-way slab. Okay, so we'll start with the numerical. A highway bridge deck slab is spanning 10 meter is to be designed as a one-way pre-stressed concrete slab with a parallel post-tension cables carrying an effective force of 620 kN. Now there is a highway bridge deck slab and the span is 10 meter and the post-tension cables are carrying of effective force of 620 kN. Okay, this was is given in the first sentence. The deck slab is required to support a UDL uniformly distributed live load of 25 kN per meter square. The permissible stress in concrete FCT. Okay, the permissible stress in concrete should not exceed 15 Newton per mm square in compression zone and no tension is permitted at any stage. Design the spacing of cables and their position at mid-span section. Assume loss of pre-stress as 20%. This much data is given. FCT is given as 15 Newton per mm square. FCW minimum we can say it is 0 because no tension is permitted at any stage and loss ratio is 0.85. So this much data is given. We start with the numerical as we have seen in the steps that we have to determine the pre-stress force and eccentricity. This is the main target we have to reach at that step. Okay, so for that we have to calculate the pre-stress in concrete at top section and bottom of the section. Okay, and for this requires calculation of movements, dead load movements, live load movements and range stresses. Range stresses means it is FCW. It means the allowable stresses or we can say the stress should be in this limit. So it is at the top, stress at the bottom range or stress at the top range. Okay, so that stresses we have to calculate and accordingly we will calculate the pre-stress and then we will find out the eccentricity, and eccentricity should be in the limit or we have to plan that eccentricity so that it will not disturb the structure or it will not hamper the our concept of one-way slab, post tension one-way slab. Okay, so this is the basic idea behind the designing of one-way slab or solving this numerical. Okay, so we'll calculate first the dead load movements and live load movements. So live load and dead load movements are to be computed considering 1 meter width of slab. So just remember or recall as we have done in reinforced slab, we have designed there for 1 meter width of slab. Okay, so in the same way we'll design for 1 meter width of slab. So we'll calculate dead load, that is MQ. This dead load is given as 25, sorry, 1 minute. So the density, so we'll calculate dead load MQ is equals to 25 in WL square by 8 is the dead load and it is calculated as 312.5 kilonewton meter, and then we'll calculate the live movement due to live load. This we simply what we have done here, we have multiplied density of concrete, that is we'll calculate this much part is W. So W we have calculated as what we know the density of concrete, that is density is equals to weight upon volume. Okay, so we don't know actual weight, so that's why we'll calculate it as a density into volume. It will gives you the W, and L square by 8 will give the quantity of live load. So we will get the live load movement in terms of B and H. In terms of B and H, we don't know what is the height of the slab or what is the thickness of the slab, and B is the width of slab. So we know the width of slab as 1 meter, so we will put it the further steps. Then the next step is calculation of range stresses at top fiber and range stresses at the bottom fiber. So here we have calculated range stress at bottom fiber. This formula you have to keep in mind. Okay. So FCT is given as 15, loss ratio is given as 0.85, and F minimum, or it is a stress due to or stress at the tension zone in prestressed concrete, so that is 0. So we will get this value of FBR, that is range stress at the bottom fiber. Okay. Hence the minimum section of now here we don't know what is the height or depth of the slab, so we'll calculate that part first. So for this we require this expression. This expression is for the modulus of section modulus. Okay. So what we have done here, as you can see, this section modulus at the bottom, that is ZB, should be greater than BH square by 6. So this also gives us the section modulus value, and this is greater than the MQ in bracket 1 minus N into Mg divided by FBR. Okay. So here it is a plus sign, MQ plus 1 minus loss ratio into Mg divided by FBR. So this is the formula. So by putting these values for H, that is unknown, so we will get the H as a 410 mm. Okay. Then we will calculate the area of slab for 1 meter width. So A is equals to B into D. So B we have assumed as a 1 meter span. Okay. So it will gives us the 1000 mm into H is height, that is 410. So we get the area. Now what we have given, or what we can conclude from the one sentence, that is no tension is permitted at any stage. So according to that, suppose this is the cross section of slab and this is height, that is 410, and here is the neutral axis. So we will get half, that means h by 2, and at the h by 2 our neutral axis will be located. So ZB and ZT is equals to the same value. Okay. So we will get that value as 28 into 10 raised to 6 mm raised to 3 or mm cube. Now we will calculate the value of Mg. Okay. Here we have calculated in terms of B and H. B will keep as 1000 and H is 410. So we will get this value for Mg. Then we will calculate the stresses at the top and stresses at the bottom of the section. Okay. In this way. If you have any doubt regarding how or from where this value came, I will recall. Just give me 1 second here. Okay, determination of pre-stress in concrete at top and bottom of the section. So from this formula we have calculated the stresses at top and bottom of the section, and these values will keep in this formula for finding out the pre-stressing force. Okay. Okay, from there we get these values, and we substitute these two values for the calculation of pre-stress force. Now how we calculate the force? It is stress into area. So we know the stress is equals to P divided by A. So we don't know what is the P. So we'll multiply these two values, F into A. And what does the F, that is stress here, it is the average of FB plus FT divided by 2. So it is average stress into area. So we'll take the average of these two and multiply it with the area. So we'll get the value of pre-stressing force, that is 3075 kilonewton, and then we'll calculate the eccentricity. E is equals to 109 mm. Okay, now as we know here, uh, we have to calculate the spacing of cables. What we have to do in the final step, that is design the spacing of cables and their position at midspan section. Okay, so we have to calculate the spacing of cable at the midspan section. So how do we calculate? We know it is a total area, or total, that is B into 620 divided by 3075 is the pre-stressing force. So we'll get this value of 201 mm. So we'll adopt this spacing of the 200 mm at center in the midspan section. So it will complete our numerical. Okay, just keep in mind these steps. Okay, these are very important, and I will give you the soft copy of the notes afterwards. So here completes one numerical, and we'll take one numerical on the calculation of the same ultimate the calculation of the uh, two-way slab, or we'll design the two-way slab. Okay, we calculate spacing of the cable and pre-stressing force in the parallel ways, like we have done in this numerical. Okay, so all the best. Thank you. If you have any doubts regarding this topic, then you can contact me. Thank you.